Soaps are potassium salts or sodium salts or fatty acids, also commonly known as soap salts, which are slightly acidic. Soap making is simple, yet the chemical reaction is complex. A solid soap is chemically produced when fatty acids, the fats and oils, and a base, a solution made of sodium or potassium hydroxide, and water, also called a light solution, mixed together react to produce soap and glycerin. Meanwhile, a liquid or a very soft soap is produced when instead of using sodium hydroxide as a base, you use potassium hydroxide. So now we're going to talk about saponification. Another name for it is soap making. There are two types of saponification processes. The first one is the cold process, where soap is made when the fats and oils are mixed with the lye solution and no external additional heat is used to make the chemical reaction. Heat is produced by itself during the reaction, which drives the soap making process forward. Complete saponification and curation period is slow, as it takes about 3 to 4 weeks. The second one is the hot process, which uses an external heat source to bring the soap into a gel-like state, and it curates much faster, being ready to use in 6 to 8 hours. This is because the external heat accelerates the saponification process and the solid soap hardens faster. Saponification can be broken into 2 steps: the breaking down of ingredients so that they are useful, and the reaction of these useful parts to form soap. So now we're going to talk about the breaking down ingredients part. Fats and oils are made from triglycerides, compounds made of 3 fatty acids linked to 1 molecule of glycerol. Triglycerides must be broken down into fatty acids and glycerol in order to make soap. Here we can see another picture showing the molecular structure of triglyceride. In addition, these fatty acids can be saturated or unsaturated. The saturated ones have carbon atoms bonded with single bonds, share one set of electrons, and have a greater molecular attraction between the atoms. That's why they're solid at room temperature. Meanwhile, the unsaturated ones have one set of carbon atoms bonded by sharing 2 sets of electrons, called the double bond, and have less molecular attraction, which makes them liquid at room temperature. Here we have an example of a saturated fatty acid and its molecular structure. This one is from palmitic acid, and this one is from the oleic acid, which is an unsaturated fatty acid. Fatty acids consist of hydrocarbon chains, which are not soluble in water, and with a carboxyl group at the end, which are soluble in water, as we can see in this picture. There are long chains of carbon, hydrogen, and oxygen atoms. The difference between a saturated and an unsaturated fatty acid is that the hydrocarbon chain from unsaturated fatty acids have some hydrogen atoms missing, resulting in the creation of double bonds. So now moving on to hydrolysis. When triglycerides are broken into fatty acids and glycerol, it's called hydrolysis, a process that breaks down fats and oils into useful parts, which happens when the triglyceride absorbs water into its components. Plain water can't fully split apart the fats and oils. This is when the hydroxide ions from the lye solution come into play. These ions help better split fat and oils apart as they attack the carbon in the carboxyl end of each fatty acid in the triglyceride, from triglyceride to diglyceride, and then finally to monoglyceride. Each released fatty acid then reacts with the sodium ion to make soap, and the separated glycerol then reacts with the hydroxide ions to make glycerin. However, unsaturated fatty acids take much longer to saponify as they have double bonds, irregular shapes, and are less compact, which makes it more difficult for sodium and potassium hydroxide to position itself for a reaction. So we can say that during hydrolysis, the saponification process occurs as soap is being created. Now the breaking down continues with the bases. In my formulas, I'm going to use both sodium and potassium hydroxide as my bases. These are alkyls as they are a compound of an alkyl metal ion and a hydroxide ion. The hydroxide ion is the most important thing as it's the one that drives the process of hydrolysis. So when sodium hydroxide or potassium hydroxide is mixed with water to create the lye solution for saponification, the sodium or potassium ions and hydroxide ions separate. This is called ionization, which releases heat. Now there are three ions available to react. So these were the acids and bases. Finally, we have the reaction process. When triglycerides break down into fatty acids and glycerols, fatty acids become available to react with sodium ions in the lye solution, making soap or sodium/potassium salts. And then the glycerol, which became available, reacts with the hydroxide ions in the lye solution to create glycerin. This is a very good moisturizer for the skin. Industries that produces soaps take away the glycerin to sell separately as a byproduct or to make their soap with free fatty acids. And then no glycerin is formed as a byproduct. With all this said, I also want to say that the breaking down of ingredients and the reaction process occur simultaneously. The last concept that I want to introduce to you today is the trace. The trace is a very important concept when making soaps. It occurs when saponification process is almost finished. You recognize it when a bit of soap is drizzled from the spatula onto the surface of the soap, which then leaves a trail for a moment before disappearing beneath the surface. A trace is the ideal moment to add additives such as essential oils, colorants, clays, etc., and later pour it into the mold. Thank you for watching the video. Please like and subscribe to my channel. Bye, see you in the next video.